Things are as exhilarating as heading around the racetrack at just under 200 miles per hour. Hi, welcome aboard the number 24 DuPont Chevy Monte Carlo. I'm Jeff Gordon. It takes a lot to win a NASCAR race, like science, technology, and math. There's a whole lot more to it than just counting laps. You also need plenty of something else. Fuel. During an average race, my race car burns 100 gallons of fuel. Guess how many gallons this car uses? None. Instead, it uses electricity. NASA is working on cutting-edge technology using electricity to propel a spacecraft instead of using fuel. To do that, NASA will use the power of math, science, and technology. But hold on, race fans, there's a string attached. Ladies and gentlemen, start your engines for this episode of NASA Connect. Hey there! Welcome to NASA Connect, the show that connects you to the world of math, science, technology, and NASA. I'm Van Hughes.
And I'm Jennifer Pulley. Today, we're at Disney MGM Studios in Orlando, Florida. We are your hosts, along with Norbert. Every time Norbert appears, have your cue cards from the lesson guide and your brain ready to answer the questions he gives you. And teachers, every time Norbert appears with a remote, that's your cue to pause the videotape and discuss the cue card questions he gives you.
Fasten your seatbelt.
On today's show, we'll learn how NASA researchers collect and measure data, recognize patterns, develop functions, and use algebra to solve their problems.
Then they compare the results and predict how the technology will perform in space. Plus, you will simulate NASA research and learn all about magnetic forces and how they cause motion.
And you know what? You're going to be doing all of this in your classroom.
It's going to be a thrilling ride.
Later, Dr. Shelley Canwright will get you hooked up to this show's web activity. Today's NASA Connect program features patterns, functions, and algebra to get you wired for space.
Did you know that NASA researchers use math, science, and technology every day to make sure space transportation is safe and reliable?
That's right, and more affordable too.
You know, NASA Connect has sent us on some pretty cool locations, but Disney MGM's rock and roller coaster starring Aerosmith is definitely a gas.
Gas? Not gas, Van. This coaster uses state-of-the-art electromagnetic motors.
Electromagnetic? You mean this roller coaster runs on electricity and magnetism?
Exactly. Electricity is one of the fundamental forces of nature that we use to make things work for us. Magnetism is the force of attracting or repelling magnetic materials. Magnets have the power to pull things toward them, but they can also push or repel things away. When you connect the power of electricity with the strength of magnetism, you can make an electromagnetic motor, like the one that gets your clothes clean in the washer. Today, we're learning how electricity and magnetism are used for what you might call another type of spin cycle, propelling spacecraft into orbit. 0 to 60.
Oh man,
2.8 seconds.
That was so awesome. Now tell me, how does a roller coaster like this relate to NASA and spacecraft? Not that I'm complaining, but I want to ride it again.
Well, okay, we will. Hang on, let me tell you. NASA is working on a way to propel spacecraft into orbit. And get this, they're using a track very similar to this roller coaster track. All right. Hey, let's propel ourselves over to NASA Marshall Space Flight Center in Huntsville, Alabama, and check it out.
Jennifer, this is supposed to be like a roller coaster? Where are the loops?
Well, it's not like a roller coaster in that way, Van, but it does use some of the same scientific principles. This is Jose Perez. He's the Launch Assist Project Manager from Kennedy Space Center in Cape Canaveral, Florida.
Thanks, Jennifer. Getting into space is expensive, and the first part of the trip costs the most. That's where this track comes in. It is used for magnetically propelling a spacecraft. Like magnets, electricity has a similar push and pull called charges. In fact, electricity and magnetism are a lot alike because they are really the same force of nature. We're just used to thinking of them as two different things. That's where maglev, or magnetic levitation, comes in.
Okay, so what is magnetic levitation?
Magnetic levitation, or maglev, is a new technology being developed for high-speed trains. Instead of running on metal wheels, these new trains float or levitate above the track.
Levitate?
Yeah, how does that happen?
Well, electromagnets in the track levitate and propel the vehicle down the track without any direct contact.
Cool, I get it. Electrical charges are like magnetic poles that repel each other and pushes it down the track.
Exactly. The magnetically levitated spacecraft will leave the track traveling around 600 miles per hour and then reach orbit using rocket power.
What kind of test did they use?
Were there any patterns in the results?
What kind of graph resulted from the data?
One of the things that we test is how much force is being produced by our electromagnets. To find the force, we use this equation. F equals m times a, where F is the force, m is the mass, and a is the acceleration. Acceleration is the increase of speed over time. We put sensors aboard our test vehicle that measure its acceleration. Since we already know the mass of our test vehicle, if we multiply the acceleration by the mass, we can determine the force. Taking those numbers and producing line graphs, we can show the forces on our test vehicle. The pattern that develops helps us predict the performance for future space vehicles.
Wow, that's a pretty exciting way to understand math. You use math every day, right?
Yes, and we also share our results with people in industry and other NASA centers. By looking at our results, they can understand how much the carrier is accelerating and how much force the track magnets are generating. Because we speak the common language of mathematics, we can share what we learn, and we learn from each other.
Well, that's pretty neat. I mean, NASA uses electromagnets and this track to help them develop new ways to propel a spacecraft into orbit. And you know what? NASA's also using electricity, magnetism, and tethers to help them propel spacecraft already in orbit.
Wait, you said tethers, like tetherball, with the pole and the rope attached to the ball?
Absolutely. Some other examples of tethers besides tetherball are the elastic string that keeps a paddle ball on a paddle, a fishing line that keeps the fish on a pole, and even a leash that keeps a dog close to its owner.
Maybe you can think of some more examples. You know, NASA has been using tethers and conducting experiments in space for years.
I'd say goodbye for her. She's gonna get burned.
You're right. In fact, in the 1960s, the Gemini astronauts used tethers to connect their spacecraft to another unoccupied rocket.
The 1960s! Far out, man. What? Over the years, NASA has learned that connecting two spacecraft together opens up a whole new world of possibilities, like propelling a spacecraft. One person who knows all about tethers in space is physicist Les Johnson, and he works at NASA Marshall Space Flight Center.
Thanks, Van. We're testing a new kind of propulsion system for space that doesn't need any rocket engines or fuel. Instead, it'll use the Earth's magnetic field to help push or pull on the spacecraft.
All magnetic objects form invisible lines of force that extend between the poles of the object. A magnetic field is the space around the magnet where you feel its force. Magnetic field lines extend and radiate between the Earth's north and south poles and between the poles of the magnet.
Basically, the Earth's magnetic field works with a special type of wire or conductor called an electrodynamic tether to push or pull on the object. The electrons that make up the electric current flowing through the conductor will experience a force when they move through a magnetic field like the Earth's. Since they're trapped in the conducting wire tether, the force will be applied to the tether and whatever is attached to it. Depending upon the direction in which the current is flowing, this force can be a push or a pull, either lowering or raising a spacecraft's orbit.
So the direction of the current determines whether it's pushing or pulling.
And the more current, the more force.
Right. In fact, NASA Marshall is working on a project called ProSEDS, which uses the Earth's magnetic field to push or pull on the attached tether. When the tether moves, so does the spacecraft.
Les, ProSEDS is an acronym, right? What does it stand for?
ProSEDS stands for Propulsive Small Expendable Deployer System. Space exploration is limited largely by the cost of launching payloads. Finding a cheaper way to explore space is always very important to us. Typically, a rocket will place its payload into low Earth orbit, and from there, propellant-fueled thrusters have to boost it to a higher altitude. ProSEDS is one experiment that focuses on the technology to cut the expense of placing a payload into its final orbit.
Sounds like ProSEDS can be a nice alternative to using rocket engines and lots of fuel.
Absolutely. Electrodynamic tethers could one day be used as a cheap, lightweight, and reliable way to remove space junk from orbit, keep the International Space Station in orbit, and even power missions at other planets.
Wow, this can get us to other planets?
Tethers offer us unlimited possibilities, Van. That's why I'm all charged up about this project.
You know, students in Baton Rouge, Louisiana are also charged up about today's classroom activity.
Hi, we're from Instrumental Magnet School in Baton Rouge, Louisiana. NASA Connect asks us to help you understand how to do the student activity for this program.
Earlier, we learned that the NASA ProSEDS experiment uses long, conducting wires called tethers. The tethers make electricity that can be used to move satellites. Now, we're going to simulate the research they do at NASA by constructing and using the Make It Go Electrodynamic Demonstration Unit, or EDU for short.
First, let's make the EDU. The materials you need: magnets, batteries, wire, and very small light bulbs called light-emitting diodes are inexpensive and easy to find. Remember, safety is our #1 concern at NASA, so be sure to listen carefully and follow the safety guidelines. Now that the EDU is made, you'll need to make an electrical current level controller for the EDU. The current controller is made using only regular paper and a set of 5 resistors. Be sure that all your wires are connected correctly. This will create what is called a closed circuit that allows the electricity to flow freely through the EDU. Now you're ready to observe and predict what happens to the light from the LED when you change the amount of electricity flowing through the circuit of your EDU. If the wires are not connected properly, an open circuit exists and the flow of electricity through the EDU is broken. As a class, discuss whether there's a pattern to describe what happens to the brightness of the light when the electricity level increases.
The EDU is a model of the actual propulsion system tested in the ProSEDS mission. You'll use the EDU to observe and understand that if a wire has electricity flowing through it, the wire can actually move if it is placed near a magnet. You'll measure, record, and graph the relationship between the electric current and wire coil movement. Then, you'll analyze the results, just like NASA researchers do.
Next, construct the coil as directed in the lesson guide. Add the wire coil along with the magnet to the EDU. Observe what happens to the wire coil's motion when the magnet is present. Looking at your previous set of test results, what do you think will happen to the wire coil when the current level increases? Change the current levels and measure and record the distance that the wire coil moves at each level. Each time you test the new current level, compare the results with your classmates. Average the test results at each current level. After you've completed testing, your teacher will get you started on graphing your data, then help you understand how to analyze your results.
Great work, class, but how can we display the data that we've collected on a graph? Think about the information we're comparing.
Now that we have our graph labeled, one person from each group should come up and graph the average distance the coil moved at each current level. This looks great. What type of graph is this? A bar graph? A line graph? A scatter plot? What was the maximum distance our wire coil moved? What current level produced the greatest movement? Why do you think this is so?
Class, can you guess which electricity level the circuit is set on based on how far the wire coil is moving?
If I run some more tests, I know that I can find out.
Yeah, let's make it go again.
Man, those kids look like they were having a lot of fun.
And learning a lot, too.
Well, just like NASA Connect teamed up with a school to learn about electromagnetism, NASA's teamed up with a university to help us understand propulsion in space.
Hey, let's head to the University of Michigan and see what they've been working on.
I'm Professor Brian Gilchrist with the University of Michigan in Ann Arbor.
And I'm Jane O'Weiler, a graduate student in Space Systems Engineering here at the university.
My students were asked to design, build, and test a very small spacecraft that will be used with NASA's ProSEDS Tether mission. ProSEDS is demonstrating a new kind of propulsion technology that does not require any rocket engines. It uses the Earth's magnetic field to help push and pull on spacecraft. ProSEDS will pull down a large, used-up rocket stage.
We named the satellite Icarus after the character from Greek mythology. As you might know, Icarus and his father Daedalus were trying to escape from Crete using wings that they'd built. Icarus flew too close to the sun, and the wax that was holding his wings on melted, and he fell into the Aegean Sea. The ProSEDS mission will be successful if it can rapidly bring down the rocket engine from orbit, which will ultimately burn up in the atmosphere, falling from the sky, just like Icarus. The Icarus satellite will pull out 15 kilometers of tether from the deployer, and the instruments on board will measure the location of the end of the tether, the end mass, and spacecraft attitude.
Did she say attitude?
Not that kind of attitude. I mean the position of the spacecraft relative to the Earth.
Right, Jane. The students designed this satellite to collect this information and transmit the data to the ground. Mission scientists will use this information to better understand the dynamics of tether systems.
To build our satellite, we used computer design tools and a lot of discussions and mentoring from experienced engineers and faculty at Michigan, the NASA Marshall Space Flight Center, and from industry partners such as TRW. After the design work, various mechanical and electrical components were purchased or built. These pieces were carefully put together, and then we were able to begin a long list of tests to see if it was going to work the way we wanted it to.
At the same time we were designing the hardware, we were developing the computer software. Not everything worked the first time, as is typical of anything new being developed. So we had to consider what could have gone wrong, read through the notes and journals to check that we did everything right, and then try again. And sure enough, some changes had to be made to get it ready for delivery and flight. Each step required careful planning to accomplish the special steps that we mentioned earlier. The tests were done here in our labs at Michigan and at the Marshall Space Flight Center.
How did you gather the data?
Electronic sensors were often used in our tests to make the critical measurements necessary to know that the Icarus satellite was still working correctly. But other data collection involved just looking at the satellite to see that, for example, our solar cells were not broken, and sometimes we had to measure how much power the solar panels could generate, or how much power our radio transmitter was sending to its antenna.
Wait a minute. They're in Michigan,
And we're at the Marshall Space Flight Center in Huntsville, Alabama. How do they do that?
Good communications in a project like this is very important. When the students were designing and building their spacecraft, they communicated with their NASA partners using presentations, written reports, and through email using the internet. Later, as we were collecting data, we dealt with the test reports that showed how the satellite and its instruments performed. By using patterns, functions, and algebra, they were able to prove to themselves and NASA that the Icarus satellite was ready for flight. Being able to understand data in the form of charts and graphs is a lot easier than descriptions. Mathematics is really like another language, a language that all of our partners need to understand to be able to work together.
How is algebra used to find the solution?
How are arrays used in algebra?
What algebraic equation shows that voltage is related to current?
Hey guys, meet Leslie Curtis. She's an engineer here at NASA Marshall.
Thanks, Van. Dr. Gilchrist is right. Mathematics is one of the most powerful tools that we have available to us at NASA. We use algebra almost every day to find solutions to our problems. This is the Icarus satellite that Jane told us about. It uses solar cells to charge its batteries. Solar cells, which convert sunlight into electricity, are arranged in a pattern called an array. One of the ways that equations can be written in algebra is also called an array or matrix. Actually, they look a lot alike. Let's compare them. Here's an example of an array used in algebra. Notice the pattern of rows and columns. Now here's a picture of a solar array. See the rows and columns again? Let's use the solar arrays on the Icarus satellite to do a simple math problem that the students at the University of Michigan were faced with. Then let's compare solar arrays with algebraic arrays. The Icarus satellite uses 12-volt batteries. Voltage is a measurement of electricity. And if we use a solar array to charge our batteries, we know from science that we need to have a solar array voltage that is slightly higher than the 12-volt batteries. So let's say 15 volts. To To calculate the number of solar cells we need for the array, we use algebra. And since each Icarus solar cell provides 0.5 or a half a volt of charge, how many cells do we need for our solar array to produce the 15 volts? If we solve for C, which stands for the number of cells, we see that it will take 30 cells to give us 15 volts to successfully charge the batteries. From this information, we can arrange our solar cells in a solar array pattern.
Cool, like 10 cells wide by 3 cells high?
Or 15 cells wide by 2 cells high.
So you see, when scientists are trying to calculate complicated equations, we often write them in the pattern of an algebraic array.
That's great. So you use patterns and algebra to determine the amount of solar cells in an array. But let me ask you this. How long does it take for solar cells to charge Icarus's batteries?
Well, that question can be answered using algebra also. We know that the charge on the Icarus satellite batteries is related to current and time. Current is another measure of electricity which is expressed in units called amperes, or amps for short. Now, to calculate the amount of time needed to charge the batteries, we use the following equation. Charge is equal to current times time. Since we want to know the length of time needed to charge the batteries, we can rewrite the equation as time is equal to charge divided by current. The Icarus satellite batteries have a maximum charge capacity of 2.5 amp hours. A typical charging current that we might use to charge the system is 0.5 amps. So if the charge is 2.5 amp hours and the current is 0.5 amps, the equation can be written this way. Time is equal to 2.5 amp hours divided by 0.5 amps. Solving for time, we can see that the time required to reach full charge on the system is 5 hours.
Okay, let me see if I got this straight. We use voltage as a way of measuring electricity when we're talking about the solar array, and current to describe electricity when we're calculating the time it takes to recharge the batteries. But how are voltage and current related?
Voltage and current are related by the simple equation V equals IR. V stands for voltage, which is usually measured in volts. I is the current, which is usually measured in amps, and R is called the resistance. The resistance is measured in units called ohms. And the equation V equal IR is actually called Ohm's law, after G.S. Ohm, a German scientist, and the unit of resistance was named in his honor.
You just wouldn't believe the resistance I got. Shocking.
You know, I think it's pretty sweet that the university students used algebra to work with NASA on the ProSEDS experiment.
Yeah.
But I don't really get the volts and amps and resistance.
Oh my.
Volts and amps and resistance. Oh my.
Get it, Dorothy?
I get it.
I just couldn't resist. Nor could we resist the chance to meet some students who teamed up with NASA Connect and are wired for today's web activity.
Hey gang, hey Norbert, welcome to St. Louis, Missouri. I'm standing here in front of the St. Louis Science Center, our museum partner for this show. This Science Center is a 232,000 square foot 3-building facility that's connected by a bridge in a tunnel. It contains 11 galleries, over 650 exhibits, an OmniMax theater, planetarium, discovery room, and live science presentations. In a moment, we're going to go inside to meet the students from the Compton-Drew Investigative Learning Center and the AIAA student chapter from the University of Washington, St. Louis. These students are going to highlight for us the web-based activity which complements this NASA Connect video program. But first, let's take a quick flyby of Norbert's online lab. There are a couple of areas of this lab worth investigating. Teachers, the Lab Manager section is designed especially for you. Here you will find scenarios and tools for integrating NASA Connect's web activity into the classroom. Another excellent resource for integrating technology efficiently into the curriculum is ePALS Classroom Exchange. As a Connect partner, it offers free web-based email and an online classroom community of over 130 countries with whom you might communicate and collaborate on class projects, such as those projects suggested in the Connect programs. Well, here we are now inside the St. Louis Science Center and waiting and ready to take us into the wild blue yonder of the internet in this Connect Show's web activity are our guest middle and university students. The The web module that they will share has been contributed by Princeton University's Interactive Plasma Physics Education Experience, or IPEX.
IPEX has created several interactive physics modules, including one on electricity and magnetism. This module will introduce you to many of the basic concepts involved with electricity and magnetism, like static charge, moving charge, voltage, resistance, and current. This site combines multimedia with built-in interactive exercises to help you better understand the concepts. For instance, you can rub a balloon on a wool sweater to learn about static electricity. Use a slider bar to see what happens with similar charges on balloons. Build and complete a circuit.
So there you have it. Take a website, add interactivity, subtract complexity, and multiply excitement. The E-solution is simple. Norbert's online lab. It's where education clicks. Bringing to you the power of digital learning, I'm Shelley Canwright for NASA Connect Online.
I'm coming. I've already lapped you once, so you really should be catching up.
No, you haven't. I passed you. Dustin.
Oh, man, I almost had you. Well, you know what? That's about all we have time for today. Van, you might have beat me at slot car racing, but you're definitely no Jeff Gordon.
We'd like to thank everybody who made this episode of NASA Connect possible.
That's right. You know what? We hope you've all made the connection between the NASA research that's used to propel spacecraft without the use of fuel and the math, science, and technology that you do in your classroom every day.
Jennifer and I would love to hear from you with your questions or comments, so write us at NASA Connect, NASA Langley Research Center, Mail Stop 400, Hampton, Virginia, 23681, or send us an email, connect@edu.larc.nasa.gov.
Hey teachers, if you would like a videotape of this NASA Connect program and the accompanying lesson guide, check out the NASA Connect website. From our site, you can link to CORE, the NASA Central Operation of Resources for Educators, or link to the NASA Educator Resource Center Network.
Until next time,
stay connected to math,
science,
technology, and
NASA.
See you then.
Bye-bye.
Here we go!
Jennifer, this is supposed to be a roller coaster?
Maybe.
I was waiting for you to say, where are the loops? You're right, man. Man.
Far out, man. How the technology will perform in space. Plus, they do something else.
This is Jose Perez. He's the launch project manager. No, he's not. Yeah, you know, Van, you might have beat me. It's like you broke your car. I was walking on it.
All right, there you go.
Where's the squirrel? Maybe.